The story is that I found these papers on arXiv and I sent them to Hardy and I said, this looks interesting, we should look at it. And with Middle Eastern cunningness, he turned it around. I now present it to him.
Exactly. And this is on record.
On record.
Yeah.
So yeah, so when I saw them, they looked very interesting, and you know the word deep. It's a hot word in machine learning. So I don't know how much machine learning this is. I think we could call it multi-layer feature extraction, mathematical properties of, or so. I don't know if it's machine learning. Yeah, but let's go through and see if we can learn something. So I have some background mainly for notation. You should know what LP spaces are. So the general LP norm, you should know, yeah, I guess you know. And the LP functions are functions with a finite P norm. If we identify functions that are equal almost everywhere mu to be the same function, then this is a norm. And for p greater than or equal to 1, this is a Banach space with this norm, so it's a complete norm space. And with you can define different inner products, but the one you know, I guess, is for L2 when this is the inner product. And with this norm, this is a Hilbert space. Yeah, and of course here mu can be some general measure, but if nothing else stated, we assume it's the real line with Lebesgue measure. Fourier transform, you should know, this is to set notation mostly. So for f in L1, let's start with L1. This is the Fourier transform, something you know. If two different Fourier transforms are the same, exactly the same everywhere, then the corresponding functions are almost everywhere the same. Lebesgue almost everywhere. If both f and its Fourier transform are in L1, then you can express the function almost everywhere Lebesgue as an inverse of the Fourier transform. You know that too. Also for L1 functions, L1 functions, we define convolution. You should know that too. Okay, how about L2 then? So L2 is not a subset of L1, so usually you say f both in L1 and L2. So if f is both in L1 and L2, then f hat will be in L2, and the norm of f will be the same as the, so the 2 norm of f will be the same as the 2 norm of its Fourier transform. Then you have Pam-Cherel's theorem, which says that there is a unique linear operator between from L2 to L2, defined by, it's a linear operator corresponding to doing the Fourier transform. Let's call it big F. It's unique for f in L2. What am I saying? No, wait. Yes. Okay, so what's going on here? Yeah, so the Fourier transform is defined for L1. In L2, you have instead convergence in the norm. You don't have this everywhere or almost everywhere result. Instead, you need to look at the convergence in the norm. So to compute the Fourier transform for an L2 function, you need to round it and do the integral and let the integral grow. And it will converge in the norm. This should be 2 here. Okay, it's the 2 norm. Yeah, the norms are the same if you compute for function or its Fourier transform, and also inner product is the same. If you do inner product f and g, you can also do it on the corresponding transforms. You get the same number.
So this capital F is the Fourier transform.
It's the Fourier, yeah. The easy, I'm just stating the full theorem. It's a unique linear operator, which is actually defined by the transform, but it has other properties. Wavelets, who knows wavelets? A little bit. Yeah. So wavelets were a very hot research topic in the beginning of the 90s. It's something related to the Fourier transform, or it's a more general thing than Fourier transform. Actually, you can express the Fourier transform as a special case of the wavelet transform. I guess there are different ways to approach the topic of wavelets, but this is at least one. So if you have a fixed L2 function psi, you define this psi AB of x by translation b by amount b and scaling by amount k. So you scale in the argument and you also normalize outside. And then you define the wavelet transform of f simply as the inner product between this function f over x then. But then there are another two variables still here. So in a sense these two correspond to, it's not frequency, but it's something, it's the parameters. There are two parameters. So it's, I guess, position and scale or so. And wavelets are used in particular when you want to zoom in on features in images, since you can change the scaling. And then you have some corresponding results for wavelets. So this is just a technical condition that two integrals are finite. Don't worry about the details, but if you define this measure here on the Borel set, mu0, it's simply the big integral over the Borel set of 1 over a squared scaled by this, and this guy comes from here. And then you define this product measure between this one and the big measure. Then the wavelet transform is a linear operator. So what am I doing? I'm now stating something that corresponds to this Plancherel theorem, but for wavelets. That's what I'm doing. So if this is the wavelet transform, it's a linear operator from L2 to L2 that preserves the norm and in a product in this sense. So these two correspond to those two for the Fourier transform. Preserved product and inner the norm and inner product. You preserve the norm and the inner product. Yes, and then if both f and its Fourier transform are in both L1 and L2, then you have an inverse for the wavelet transform. You do an integral over the a and b parameters with, remember, with respect to this guy here. I mean, if you didn't see this before, the details are not so important, but so wavelets are a generalization of Fourier transform where you don't look in frequency, you look in position and scale, so to speak, instead of frequency. And that's one thing, and then there are corresponding results to the Plancherel thing for wavelets. Yeah, and then another two definitions that we need later. A rotation group in RD, it's just a set of orthogonal matrices. Rotation in RD. One more thing we need for later. If you have two metric spaces that can come from normed spaces, of course. The function is Lipschitz or Lipschitz continuous if two input points are close, then the corresponding two output points cannot be too far away. So if x is close to y, then there must be a constant here, finite, such that the corresponding output points are not too far apart. Then the function is Lipschitz continuous. Yeah, couple more things. So now I'm starting to, so far it was background, now I'm starting to enter the actual papers that I'm supposed to present. So even more notation. Let's introduce this notation for translation. So TAF is just you translate by A. So I could have used this already for the wavelets. I mean, translate by A. We did that for the wavelets. I could have used this already in this notation. And this I of F is just reflection plus conjugation, complex conjugate. Okay, so let's define something that's called a semi-discrete frame, and this is now like one more step generalization from wavelet. So we have Fourier transform wavelet frames. A semi-discrete frame is based on a collection of functions that are in both L1 and L2. Not any functions, they have to fulfill this criterion here, but for now they are any function. And then the collection of functions you get by doing this operation, reflection and conjugation, and translation on these, indexed by I. So this can be an infinite set in general, countable but infinite. And B can be continuous, so for each B here. So this B is, it says A here, but here we plug in a B, so that's the translation. This possibly infinite or even uncountable set actually, since B is not necessarily countable. It's a semi-discrete frame for all L2 if there are constants A and B, such that, I guess we can look here, such that if you do the convolution between something is missing. It should say for each F in L2. What is F here? Yeah, it should say here for each F in L2. Such that for each F in L2, if you do the convolution and you take the 2 norm square and you sum over I, and for any B then, no, not for any B, sorry, not for any B, it integrated over B. You get something that's bounded between B times norm of F squared and A times norm of F squared. Yeah, these functions are called the atoms of the frame, I didn't say that. If you have this result and A and B are the same number, then you say the frame is tight. If they are the same and also 1, you say you have a Parseval frame. So obviously for a Parseval frame, you preserve all energy. If you filter F against all these different I's, you filter over B here, then you preserve all the energy in F. So this result is similar to what did we have for the Fourier transform we had. So this is more general. Here we say it's between two endpoints, not too far away. Yeah. For it to make sense, of course, you don't want A to be 0 and B to be infinite. I mean, it's understood it's not too far away, A and B. And even equal or even 1. Yeah, this is not important, but you can define something that looks a bit like an inverse transform. You can call it a frame operator. So if you compare, I will not spend so much time here, if you compare this to the inverse transform for wavelets that we had here, for wavelets you actually get the function back. Here instead you get a mapping or an operator that's invertible, but you may not get your function exactly back through doing this. Right, yeah. Let's keep that. Okay. So I'm now in the papers, but so far haven't stated any of the results. Because first I did my own background, now I'm doing their background. So I'm still on the part where I do the background they give. And I let you know when I state the result that actually comes from the paper. So this is still background, because this is background for so-called scattering networks that were introduced in 2012 by Stefan Malla. So this is for you who have seen the wavelets literature, this was a big name in the 90s in the wavelet boom or so. So he's still around. So this here is something that looks a bit like a wavelet, but instead of doing translation you do rotation. So let's look at it. So you have a fixed function that's both in L1 and L2. Then instead of translating we rotate. So here you rotate x. So this is just an orthogonal matrix RK. Or you have a finite set of rotation matrices or orthogonal matrices RK. And you apply each of them indexed by k. So you take an input point and then you rotate it. And then you scale. So scaling you have like for wavelets, or not exactly like for wavelets actually. For example, in wavelets you have the square root of here, and yeah, but something similar to wavelets. Scaling you have, but instead of translation you have rotation. Otherwise it looks very much like a wavelet. So this is indexed by j from minus big J. So this is a fixed constant, but then every other j from this on, I mean up to infinity. But k comes from a finite set. So for this is for small j bigger than minus big J. And then let's also define what we get for small j equal minus big J as a special case. And that special case is that you don't rotate, but you still scale. It's not a special case, it's an exception. Yeah. As an exception from this, for j equal minus j, you don't rotate, but you still scale. And then you cannot choose any function psi. You need to choose it such that this forms a semi-discrete frame in general, and in particular a Parseval frame. And Parseval, remember, was when you preserve all the energy in the function. stop me because I'm basically bombarding you with notation, and it's very hard. I mean, I complain in our internal seminars when there are lots of equations.
That's different.
Yeah, this is there are lots of equations. Yeah, stop me if you have questions. Let's go on. So I'm still on the topic of scattering networks based on semi-discrete frames. So how do we use this? So we have some input waveform or signal in L2. So what a scattering network now is defined by filtering, scaling, rotation, and the nonlinearity. And the nonlinearity used is the what's this called? Amplitude. Yeah, complex amplitude. Amplitude. If it's a complex number, it's the amplitude.
Yeah. Modulus.
Modulus, thank you. That's the word I was looking for. Modulus nonlinearity. So is there a connection already now to deep networks and neural networks? Yes, a little bit, because you do linear operation, that's filtering. You do a linear operation scaling. You do rotation, and you do a nonlinearity. It sounds a little bit like a neural network. Okay, and then the features of the nth layer. For n equals 0, the features are the function filtered by psi 0, and psi 0 was this guy here. So it's psi, but no rotation, only scaling. And I guess it's the smallest scaling, since from this point on j will be bigger than minus j. Yeah, so it's 1/2j. No, this is difficult. No, what is it? It's the smallest number. No, biggest number. It's biggest number. It's the biggest number.
Yeah, but it's the smallest dilation. Or
Yeah.
The other way around. Yeah.
Yeah, the other way around. Exactly. Yeah. So that's the first layer. The second layer is that you take now psi 1, and psi 1 is then it's the collection of these guys over both j and k. Psi 0, then you didn't rotate, but you still scaled. Yeah, so this is a set. It's overall. Sorry, yeah. Psi 1. Now I'm a bit. Do you vary? Sorry, I need to check. No, this is only. Yeah, it's a set, but it has only one member. Sorry for the confusion. Here you actually only do this one. Psi 0 is only one. It's only one function. Yeah. But here it's a collection, because here you vary j and k. The scaling and rotation you vary. So here you get the set. And you also first you filter with this rotated and scaled psi. And then you filter again with psi 0. So you can view psi 0 as the final filter that generates your output, so to speak. And then next collection, you do this once more. So each time you add a layer, you do the filtering, modulus, filtering, modulus. Let's look at the illustration now. So the final layer is no, it's not the. Is it the final layer or the first layer? I guess it's the first layer. The first layer, there you only have the filtering with psi, what I call psi 0, And then you have the first layer, then you do the filtering and modulus, plus filtering again with size 0. And here you do filtering modulus twice, and then size 0, and 3 times and 4 times, and then this grows as much as you want. And then Mala, in his paper, already had a translation invariance result that looks like this. So this notation is not defined before, but I think it's obvious what I mean. You take a member of any of the sets, for example this one. So this is a set, so I take one member, computed based on F, and then I take the corresponding member, but computed based on a translated F. So pairwise. Compute based on F and then translated F. And then do it for all members of a set. And then, so this guy here is to be read as the sum over the square norm between square L2 and I forgot the 2 here, but the square the L2 norm over that set, and then you also sum over the different sets. So this n here is over the different. And in total, if you let the number j grows, and j was the smallest scaling, corresponding to the smallest scaling, we can let be even smaller if we like. Then let's see now, what does this mean? The features in the limit they are preserved or they are not affected by translation. I guess that's what it says. And then when is this good? It's good, for example, if you want to do text recognition or something where you're not interested in the you have an object and you only want to know which object. You're not interested in knowing the okay, we're talking translation, so the position of the object here then. But of course position can be vertical and horizontal position, for example. Yeah, and I showed you this illustration. So this is a scattering network. Yeah, so it looks a bit like a neural network, since you do filtering, and then you do nonlinearity, and then you do filtering, and then you do nonlinearity. Okay, so is there now a reasonable connection in general to deep networks or deep neural networks? So forgetting for a moment about frames and scattering networks, what are properties of deep convolutional neural networks? We said this already. You do some filtering. You do some nonlinearity, and then something that we didn't do yet is some kind of pooling or pooling. I don't have it. Averaging. Averaging is a special case of pooling. They use a more general term that you could call pooling. Averaging is a special case. So now I'm starting with the papers that I'm presenting. So this is their definition. Deep convolutional neural network is of course not their definition, but the observation here that what's going on, you have filtering, you have nonlinearity, you have pooling. So let's do this based on a semi-discrete frame then. That's where we're starting now. And I think I'll show you the illustration first, because then I will explain the notation. So now we will do something similar to the scattering network, but even more general. So still single out a filter that you use for the actual feature generation, And then you have, if you want to call them hidden layers or something, perhaps. You have operators that are built up from several stages of nonlinearities and filtering. You cannot see here what this is, but I will explain. And so in the scattering networks you had only modulus here. Here you do something more general now. And that comes soon here. Yeah, this will be very hard for you to remember all the notation, but you have the slides. So let's say this big lambda is it lambda or gamma? It's lambda. Big lambda indexed by n is a countable set just of indices. It could be integers. Something that we use as an index. And then we have a set of atoms indexed by this small lambda at stage n. And then from these we build a semi-discrete frame as before. So you take these, you do the reflection plus conjugation and translation. Now, something that's new now, you replace the modulus nonlinearity by a more general nonlinearity M. So this is a general operator, nonlinear operator, but it's Lipschitz, and that's why I needed to define Lipschitz. So it's nice to a certain extent. It's a nice operator, nonlinear but nice. M is this corresponds to before when we did the modulus nonlinearity. And then we introduce also another operator that can be nonlinear, and this is the pooling operator that we didn't have in there. So if we go back and look at the scattering network, the only nonlinearity here was the modulus, and there is no pooling here. Now we do two more things. We do something more general than modulus, and we introduce a pooling operator. And the collection of the frame, this nonlinearity and the pooling operators, they call a module sequence. That's not so important perhaps. And finally, now I call this the pooling operator, but I guess this is the pooling operator. This guy is involved in the pooling. So pooling is now defined as if you have a function in the input, h of x, the output is generated by here you put h through the pooling operator, the p. I called it the pooling operator, so let's stick with that. And then this is now a function of x. You don't evaluate that function at x, you evaluate it at Sn times x. So here is a scaling, and then you scale outside also, like for frames. You remember they also did scaling inside and outside. And this is now the pooling. So this could be averaging. Averaging could be what you do here actually. P is general enough to. So that's why we can call this pooling then. It can be averaging. And these numbers here are different for different n, but they are greater than or equal to 1. So special case is that these are all 1, and this is just a linear filter. That's a special case. Then you can do averaging in x and over x. Yeah, even more notation. Yeah, so to define this operator notation then. Yeah, where were we? We have the frame. We have the two non-linearities M and P. We have the pooling operation based on the pooling operator, if you like. Let's put everything together. So the nth layer is defined by an operator u that takes an index from the index set. Index set, let's say pick one index. And a function h. Actually in the network this function comes from the previous stage, from the previous layer. But some input, so to speak, h. And then you do the n nonlinearity. No, you filter. You do the m nonlinearity. So this could be filtering plus modulus. And then you do the polling as defined here. And let's call what's going on here. Let's call that un. So un is an operator that takes the index and an input. Let's use this notation then. So you can also view it as an operator indexed by the lambda. So you have a set of operators indexed by lambda, and then you apply it on h. Even more notation. Yeah. Some notation. To make things even more complicated, each of these index sets could be different. I mean, this is an unnecessary step of generality. I could have skipped that, but they could be different. So let's pick now a sequence of indices picked from the different index sets. So that defines a path through the network. You will see that soon. So it's a path through the network. So now the operator, so this is an operator corresponding to the nth layer. This is the operator corresponding to a whole path. Yeah, so it's just that you apply this operator n times. And yeah, now of course the first time you apply it is on the input f. And then now I think, yeah, let's look at the illustration again then. First time you apply it, okay, no, actually you need I need one more thing. Yes, there is one more thing, namely you single out one of the g functions to be feature generating. So you say one of them is special, and that one is the feature generating filter. And the notation for that is then what is this called? Any Greek? You know Greek. C. Yeah, you're Greek.
Should be.
She. Thank you. She. Where was I? You single out one of these, call it she, and that is now the output generating filter, feature generating filter.
So that is one path.
For one path.
Yeah,
in each path you single out, so you have 1, 0, 1, 2, and so on. Yeah. So you apply all the operator for the nth layer, and then you do one more, namely you do the filtering with the sheet to generate the feature corresponding to that layer. Yeah, I didn't define that, but we have that. So the features of the nth layer corresponding to different paths through the network will give you different features in the nth layer. So it's a collection over different paths. And I think this is not This is not an assumption. This is a result of from. Let's see. Is it a result or an assumption? I think we already.
We talked about the frame
Follows,
condition.
from semi-discrete frames.
Yeah,
Right.
exactly. It follows from the fact that we assume a semi-discrete frame where we already have the condition, and then from that it follows. This follows then. So this is an energy preservation result corresponding to this network structure, or this network that we're building. And this is again the network. Okay, now to the so this is something that they build. They build this network structure in the paper, and now they have two main results.
So when tight frames mean possible, they will ask for the 2 points. The distance between that two will remain almost same if you transfer the points.
Yeah, I guess so. I mean, they could be tight. Right now, they haven't. So for the scattering networks, you assumed parseval frames.
Yeah, then it is same.
Yeah, they haven't assumed that yet, as far as I remember. They are still general. And they have two main results. They have one on translation invariance and one on deformation sensitivity or invariance. So let's look at them then. So there is one more assumption here, namely the pooling operator and this generalization of the modulus operator, they commute with translation. That's an assumption. So you can do them in any order. Then you have one result, namely that the fit.
Is it a hard assumption or?
I don't know. It's just an assumption in this result. I haven't figured out how restrictive it is. So the features in the nth layer evaluated on the translation of f, they are equal to this as a set. It's equal to features in the nth layer with no translation, but with the translation. Instead of doing a translation on f and then evaluate the feature, you can skip translation on f and do it on the features. That's one result. And then a condition that comes from the Fourier transform of these feature generating guys. We don't need to worry about that, but there is a condition. If that's fulfilled, then you also have this preservation or translation invariance result. So let's compare it to what we had for here. You have two things. One, it goes to 0, and two, you have something asymptotic here. Here you don't have nothing goes to infinity here, actually. But also this is not 0. Although it's the same, it's the same result, but for these networks now. But you don't have, nothing goes to infinity, and you have instead a concrete bound. But on the other hand, you can make this go to 0, namely since you can have all the scaling factors to be bigger than 1.
But what is Q there?
Q is the path.
Ah,
Yeah.
okay.
So it's as a sum over all the paths through the network. So as a sum for at level n, summed over all paths in the network, the features are not affected or almost not affected by translation. And the bigger you have this guy here, the less, since this you can make this go to infinity.
We need to see your own choice, right? So
It's sorry.
we can choose it.
Yeah, you can choose S. Yeah. And they have one more result that they call deformation sensitivity. Actually, MLRG for scattering networks, MLRG also had a similar result. I didn't include that because then I would have needed even more definitions. But I include this one. So this is in these new papers, and it's invariance relative to time frequency deformation. Defined like this: you take f, you translate by something that can depend on x. It's a non-linear time. If you want this to be time, then it's a non-linear time shift, and a non-linear, possibly non-linear frequency shift outside. And if f is of finite bandwidth b, there is a c. There are additional assumptions that I would need, I think, 2 slides to state, but additional assumptions. Then you have this kind of sensitivity or invariance or robustness result, I guess it should be called. You have robustness toward deformation, namely the difference between having f or a deformed f in the features for f and deformed f. The distance between is not bigger than something that depends on how big as the soup norm. How big as measured by the soup norm is the time translation and the frequency translation times how big is f. And here bandwidth comes in here. B is from bandwidth.
One question, do we need to have a finite bandwidth? So what would happen if we have a finite bandwidth, but outside that B, then the signal in the frequency domain decays exponentially fast, for instance?
That will probably work too, but then you would need something else here.
Yeah, the effective bandwidth or something.
Yeah.
I guess. Could put that.
Okay.
I don't know.
You wouldn't get bandwidth in as a parameter.
Because it's very similar to some results of reproducible Hilbert kernel space, where you have similar condition, but then there are some results showing that you don't really need to have finite bandwidth.
I assume that will work, yeah, but I guess then this is not as simple. I mean, here you only get the bandwidth times. Finally, we had translation invariance, deformation, robustness, and now how about energy propagation in these networks? For energy propagation, they consider a special case, which is a little bit like going back to scattering networks. What am I talking about? First, you have the scattering networks from MLRG, where you did this modulus. Then these authors generalized to general nonlinearity instead of modulus, and also pooling that can be nonlinear. Now they take their structure and they go back to something that looks more like scattering networks, namely no pooling and modulus. But still using the same language with Q denoting path and so on. Then we define the energy decay, or the energy in the nth layer features is just the sum. Yeah, it's the sum of the energies in the features of the nth layer, big N. It's just notation. Oh yeah, here I illustrate that this special case, but it looks like a scattering network because again you have modulus. Filtering plus modulus. And here are conditions, so let's not look at the conditions, let's look at the result first. So the result for energy decay is this. So the energy in the nth layer is less than or equal to, B is not bandwidth, it's something else now. Energy in the frequency domain, in integral. No. The integral would be the energy in the frequency domain. And then something here, which is 1 minus something that looks like something that looks a bit like this. So it's 1 minus that, so it looks a bit like that. And actually here is an illustration. Yeah, let's look here. So if this is the energy content in f hat, you multiply by something that looks like this. And the higher the layer, the more zero this will be. The less the result will be. You see, the result you will have removed more and more energy. So the higher the n here, the smaller is this product. So as n grows, you have less and less energy in that layer. It's not easy to see here, but if you consider what's going on, then you see that. Yeah, and for this result there were conditions. Let's not go through them, but you have, for example, the number b comes from here, from the conditions. So there is some number b here that you plug in here. Also, so this is a concrete frequency decay result. You also have, in general, the frequency in the nth layer decays polynomially, I guess. What do you call this, polynomial? N raised to... with n it's polynomial, isn't it? Yeah, with n it decays polynomially for in general. But then you can, of course, all this also depends on which atoms you choose for your frame, the G's. So there are ways you can choose them. For example, if you choose wavelets, or a class of wavelets, there are additional conditions, then you can have energy decay that's exponential instead. And that's a separate result they have. I don't include it explicitly. So for any frame atoms that fulfill the discrete frame criteria, you have this energy decay, but then you have special cases where you can have exponential decay. And this was an illustration we looked at. Yeah, and this is one more. Okay, and what does this lead to? As a consequence, you also get this energy preservation result when you sum over the layers. And then one more result. Okay, so a question you can ask, how many layers do I need to preserve most of the energy? So that the features represent most of the energy in the input. In particular, how many layers do I need to preserve 1 minus epsilon, also all energy except epsilon, yeah, in this sense. Then you need to choose n bigger than this number. Yeah. Of course, this also comes from, no, from here. And then as examples, they have, in general, if you want to preserve 99% of the energy, in full generality you need 200 layers. But then you can select special classes of filters so that you only need 11 layers or 14 layers. Last slide.
One question, why do we need to preserve all the energy? I know that they didn't answer that, but no, that's just a discussion. why do we really need to preserve all the energy? I can imagine that if we had at the very first stage, if we had a good representation, then we need to preserve all those energies, so as all the information.
Yeah, I guess one answer is so why do you want to have these features? Let's say you want to do inference based on them.
Mm.
Then you want a sufficient statistic of some kind. And that's not necessarily the same as preserving the energy. You want something that's sufficient for your purposes. But if you're doing some image transform or so, and you want to go back again to the function domain, or if you do video coding or so,
The autoencoder kind of.
yeah, then it makes sense to preserve the energy, because otherwise it feels like you have lost something that you can never
It's
recover.
like data compression.
Yeah. I mean, even in simple JPEG compression, you actually throw away some energy, and that's part of the compression. But you also have to keep track on how much energy you throw away, so to speak. So I think the way, so the examples they have all come from image feature, actually from written symbol identification examples. So I think they have that in mind a little bit when they comment on. Because of course this is also, you can say, it's just a mathematical exercise also, with no consequences other than fun mathematical consequences.
No, but at least in the case of scattering transform, it became very interesting because it went on to show performances which were close to, say, ImageNet or ConNet in many cases. Of course, in many cases it didn't work as much, but it still tried to catch up. So that's why the scattering transform, and you don't have to train anything basically.
Yeah.
So it was
And
quite
then also
nice.
I've seen, so I mean I haven't spent so much time, but I've seen, Mala, you can look for lectures by him, where he tries to connect this general translation and rotation invariance to why deep networks work so well, because they are very good at being translation in the general sense translation invariant. They are very good at capturing things without robustly capture features. So you can go and look at his lectures or his talk on this. Probably several of you know it already.
I mean, I attended this IEEE summer school on deep learning where he had given a similar talk, but he has been giving that talk all over the place. But then so the idea is to build more and more invariance as layers.
Exactly. Okay. Thank you.
Thank you.